Hey guys, maximum mass of a dead star. New paper here. Uh, I don't want to read the whole thing out, but I'll read the important points here. You guys can read it for yourself. Being, this is a new concept. Still, I mean, I've talked about dead stars quite a lot over the past 8 years. But for newcomers, I think it's important for them to understand that there's a difference between dead stars and stellar metamorphosis and dead stars and the dogma. The dogma's dead stars are white dwarfs. To them, a white dwarf is dead, and here are the properties, some properties for you. It has a mass comparable to the sun, it has tens of thousands of degrees Kelvin on its surface, it is extremely dense, it rotates rapidly, and has a strong global magnetic field. And that's very strange. From, I would say, a common sense viewpoint, if you look at a campfire and you see that it's a young campfire, you see the flames are big. It's really hot. It has fresh fuel to burn up. And the flames can rise up and, it's really visible. But a campfire that's dead, okay, doesn't have flames. It doesn't have glowing embers even. The coal and the ash has completely used up all its fuel. It's already been oxidized. And you can even, place your hand on top of it, given, all the coals have burned up, and it's basically chemically done. The oxygen is already combined with the carbon. That being said, it's common sense to look at a dead campfire as one that no longer has flames. It's just dead. But in astronomy, they have it completely backwards. They think a dead star is a star that is tens of thousands, sometimes hundreds of thousands of degrees Kelvin on the surface. Temperatures so hot that they can ionize the most stable, I don't want to say stable, but the hardest to melt materials, say like tungsten or iron, refractory materials, it can ionize that. Not only can it take the metal, melt it down, boil it, it can take a metal from its boiling state to its vapor state, and from its vapor state all the way to its plasma state. That's how hot white dwarfs are. And that's very strange to look at nature like that. Which is why I continue to work on the theory, because I think that if you have a dead star, it's not going to be composed of material that can ionize iron, which is a refractory material. A dead star is going to be composed of rocks and minerals. And if there's any metals in there, they're not going to be ionized. They're going to be at their lowest enthalpies. They're going to be stable, solid, cold matter, because the star is going to be genuinely dead. Same thing with its rotation rate. Now, young stars have very high angular momentums. They spin with so much mass and so much velocity, angular velocity, and that just shows that they're young. When they're born, they spin really, really fast and with a lot of momentum. But as they age, they slow down, they lose their mass. So not only does their angular velocity decrease, but their mass is lost too. So we should expect dead stars to be spinning really slowly and be a lot less massive than the young ones. And luckily, Venus also fits the bill, because Venus is, you can literally walk on the equator. Well, you can't physically walk on the equator because it's too hot. It's like 900 degrees on the surface. But let's just say it had a habitable atmosphere. You could walk on the equator about, what was it, like 4 miles an hour? I don't know how fast that is in kilometers an hour, like, what is it, like 5-6 kilometers an hour? I don't know. But you could walk on the equator and watch a permanent sunset or a permanent sunrise. That's how fast, that's how slow it spins. That is a perfect candidate for a dead star. Plus, it doesn't have a strong global magnetic field, meaning there's no fluid, liquid interior. It's mostly been solidified. It's had a lot of time to die. It's a dead star. And I use its mass, say 4.867 times 10 to the 24 kilograms. And then I look at the Earth and I think, well, Earth is going to lose that much more mass when it dies. So, and Earth is about 5.97 times 10 to the 24 kilograms. So I just rounded it up to 6. So 6 times 10 to the 24 kilograms. That's 6 sextillion tons of rock, metal, and other materials. And the reason why I wanted to say there's a maximum mass is because it's one variable that we can use to determine if a star is alive. It's very interesting that I had noticed this. Here's the graph. You guys can look it up yourself. I have it linked to the bottom. Now, the mass isn't quantified at the moment. It's still a qualitative understanding. The high mass objects are up here, the low mass objects are down here, clearly. So I arbitrarily set a line right there for representation purposes, and I set it around where the stars are active to where they're dead, right in this little area right here. Yet that very top transformation curve up here, it links right about there where that arrow is, and that's about where the maximum mass would be for a dead star. That being said, if you have a star that's anywhere up here in mass, you have a star that is active, meaning it has a magnetic field, it has fluid motion in its interior, it's spinning rapidly. Rapidly meaning at least probably the rate Earth spins at, which is 1 rotation for every 24 hours. It probably has water on the surface if it's more massive. It has a gaseous atmosphere. But that being said, the top portion, the portion where there's more mass available, which is above 6 times 10 to the 24 kilograms, all of those we can guarantee are active stars. They're not dead. But the interesting part on the bottom, I can't tell from this single variable, because there might be stars below that mass threshold that are also dead or alive, meaning they're more or less a Schrodinger cat star. We don't know if they're active. We don't know if they're alive or dead based off that one variable. But that variable is the threshold. Meaning you're not going to find a dead star that's more massive than that threshold. You're not going to find dead stars up here. These are all stars that are alive. Now, that gold area, that's just the area that sits below the Taylor threshold, which means possibly that this area right here is where stars that are chemically and physically active will never host life, which means they'll become sterile worlds. Just imagine if we were to take a spaceship up, in the future, and we find an ocean world, and it's like there's no life on it. It would be the eeriest thing ever. I mean, the largest, there wouldn't even be like microbes. It's just like almost completely sterile, completely eerie. If you go out into the ocean, if you pick up a bunch of seawater and you put it under a microscope, you're probably going to find little creatures swimming around. But if you do that on like a sterile world where it sits inside a little gold area, it wouldn't have any life. But anyways, I'm going off topic here. And the reason why this threshold is important is because I gave some examples here. I outlined the TRAPPIST evolved stars. You have 1G, 1C, and TRAPPIST 1B, F, E, and D. And I arbitrarily set it at 6 times 10 to the 24 kilograms, which is, I didn't put Jupiter masses in here, but I calculated it. I should have put Jupiter mass in here. But basically what it amounts to is a lot of the graphs I have available are in Jupiter mass, and the objects that sit above that 6 times 10 to the 24 kilogram are TRAPPIST 1C and 1G, meaning these two objects right here are probably active. They probably have water oceans, they probably have thick atmospheres, and they probably have large global magnetic fields. The objects down here below that threshold, we do not know if these objects are active. We do not know that. They could be dead or they could be alive. So just using one variable, it makes it to where we can say, oh, well, it's definitely alive, or it's dead and or alive. We don't know. And as far as I can tell, I haven't seen anybody write about something like this anywhere. So I thought, might as well throw it out there. Of course, it's up to change in the future. I don't know if the actual threshold is going to change. The only thing that would really change it is if we find dead stars that are more massive than that 6 times 10 to the 24 kilogram mass that are dead. We'll see. We'll see what comes of it. All right, you guys, take it easy.